Am I audible, sir?
Yes, you are.
Okay. A very good afternoon to everyone. The speaker of this session is Dr. Swapnil Srivastava, Assistant Professor in Mathematics, Ewing Christian College, Prayagraj, and Secretary, Professor B.L. Sharma, Higher Mathematics Trust. Dr. Srivastava is also ex-faculty of Mathematics in Sam Higginbotham University of Agriculture, Science and Technology, Prayagraj. He has graduated and post-graduated from the University of Allahabad and worked as a research scholar with Professor Ramji Lal in University of Allahabad and published a good number of research papers in reputed journals of international fame, and also published 2 books, A Fundamental Approach to Operations Research and Applications to Linear Algebra with Dr. Ajit Paul as co-author. So, on behalf of organizing committee, I welcome Dr. Swapnil Srivastava to grace this session as resource person. Dr. Swapnil Srivastava, please take over the dais.
Thank you, sir, for such a kind words. Am I audible?
Yes, sir.
Okay. So today I will speak some results related to Cello theorems and 1 or 2 examples or propositions on solvable groups. If I'm saying that I'm talking about Cello theorems, then what is Cello theorem? Yeah, what are Cello theorems? We have to understand. In the field of finite groups, the Cello theorems are collections of theorems named after the Norwegian mathematician Peter Ludwig Cello that give detailed information about the number of subgroups of a fixed order that a given finite group contains. The Cello theorems form a fundamental part of a finite group theory and have many important applications in the classification of finite simple groups. This is because Cello theorems give a method for using the prime decomposition of the cardinality of a finite group G to give statements about the structure of its subgroup. Essentially, it gives a technique to transport basic number theoretic information about a group to its group structure. From these observations, classifying finite groups becomes a game of finding which combinations or constructions of groups of a smaller order can be applied to construct a group. It means that here today we will talk about numbers and we will talk about natural numbers and playing with these numbers. So now I am coming to the statements of Cello theorems and some results related to these theorems and some applications. Today is 29th. And now I'm coming to Cello Theorems. Basically, Cello has combined three results: Cello first theorem, Cello second theorem, and Cello third theorem. These are well-known theorems. First, I will state Cello first theorem, and after that, we will discuss much more results. So what is the Cello first theorem? So if we are talking about Cello theorems, it means that we are talking about finite groups. Finite groups means a group having finitely many elements. Coming to that, let G be a finite group and P to the power R divides order of G where obviously where P is a prime. Then G has a subgroup of order P to the power R. I'm not going to prove this result. I'm only stating this result, and we will use these results. Some corollaries I want to state here related to this theorem. That is, for a particular case, we can say that of this theorem, K if R is 1. It is, let G be a finite group and P divides order of G. Then G contains an element of order P. And one definition which I want to define here, that is definition of a P group. What is a P group? So group G is said to be a P group if order of each element of G is a power of P. Obviously, here P is prime, where P is prime. Can you give me one example of a P group which is different from ZP? The question is quite simple. An example of P group. Yeah, good, Piyush. It is Q8, whose order is 2 cube, and 2 is a prime, so it is a P group. D4 is another example because order of D4 is 8. Is it? But here I am not saying that order of a P group is always of the form P to the power R. Different from ZP. Can anybody? So you have given that answer is simply V4. You can say that Klein's 4 group. You can here say that Q8. Somebody has said that D8. So these are examples of P groups. So these are P groups. Here we can say that P is a 2. So these are examples of 2 groups. Okay. So here I am coming to one more result also, which is a corollary of the Cello theorem. That is what? A finite group G is a P group if and only if order of G is equal to P to the power N for some N. And I'm coming to one more definition. That is what? A maximal P subgroup of a group G is called a Cello P subgroup of G. Means that here one result also I want to recall that let G be a finite group then G has a Cello P subgroup which is of order P to the power R such that P to the power R divides order of G, but P to the power R plus 1 does not divide order of G. So here I have talked about finite P groups, finite groups, but we can think about infinite P groups and also Cello P subgroups in an infinite group. I'm just writing this as a remark. Here we are going to study about finite groups. But one can think about infinite P groups and also Cello P subgroups in an infinite group. Okay. So now I am coming to one example of a infinite P group, some example related to this. Number one, consider G as a Cartesian product of ZP infinitely many times. That is, G is a ZP cross ZP up to so on. And I am going to define the one binary operation from G cross G to G such that plus Y, that is, one can define as X1 plus Y1. Frequently we are using these symbols, product X2, Y2, and so on. Or another way also, we can write it X1, Y1, X2, Y2, and so on. Endless. Then it is easy to see that this G is a group. So here we can see that G is a group with a respect to binary operation which we have defined here. And more one thing, whose every element of order P. So we can say that, so G itself Cello P subgroup. Now I'm going to define another example of a infinite group which is not a Cello P subgroup itself, but it has a Cello P subgroup. So another example, it is what denoting it as P. P is a set of roots of unity, that is, Z belongs to complex number such that Z to the power n is equal to 1 for some n belongs to Z. You can see that this set forms a group with a respect to complex multiplication. Now, I'm considering a subset of P, it is Z belongs to C, such that Z to the power P to the power R is equal to 1 for some prime P belongs to Z and R is also Z. So it is quite obvious that one can see that H is a subgroup of G, and order of every element of H is some power of P. So H is a P subgroup of the given group P. My natural question is that, and I'm leaving it as an exercise, that what is Cello P subgroup? So what is Cello P subgroup of the given group is capital? One more exercise which I'm giving to all of you, that if a group whose order is suppose 24, then it is easy to find that it means that is 2 cube into 3. Then we have Cello 2 subgroups and Cello 3 subgroups in group G. And what is the order of Cello 2 subgroup? The order of Cello 2 subgroup, good Niharika, that is a order of, suppose it is P, then order of P is 8, that is 2 cube, because 2 cube divides 24, but 2 to the power 4, 16 doesn't divide 24. So we have a subgroup of G having order 8, and it is maximal. So it is a Cello 2 subgroup. Suppose it is Q. So what is the order of Q? It is also quite obvious that order of Q is 3, because 3 divides 24, but 3 square doesn't divide 24. So we have a Cello 3 subgroup whose order is 3. Now I'm coming to one more proposition. It is, today I am stating only results and recalling the theorems related and results related to the Cello theorem. I'm not going to prove any result regarding Cello theorems. If anybody want to see the proof, of these results, they can see the book which we have said earlier, that is Algebra 1 by Professor Ramjilal. So now I'm coming to another result, that is, let P be a Cello P subgroup of group G, then GPG inverse, just okay. So let P be a Cello P subgroup of a group G, then my voice is coming. Okay. Yeah. So let P be a Cello P subgroup of a group G, then GPG inverse is also a Cello P subgroup, where G belongs to this group G. And this result is true in infinite group also. Means I'm writing one remark related to this result. This result is true if or it's true for finite as well as for infinite groups. One more result which we will frequently use by solving the concept of solvability, or the group is solvable or not. That is what? And I'm saying that it is also a corollary of that. The above proposition which I have told earlier, that if there exists, there is a unique Cello P subgroup of G, then it is normal. And this result is also true for finite and infinite group. And one more result, that is the intersection of all Cello P subgroups of the given group G is normal in G. And one proposition, that is every P subgroup of a finite group, okay, is contained in a CLOP subgroup. And this result basically, here I am taking that every P subgroup of a finite group is contained in a CLOP subgroup. This result is not only true for finite groups, but this result is also true in infinite groups. And with the help of John's lemma, we can prove it. I'm not going to prove all these things. And one more proposition which I want to recall, that is, let P be a CLOP subgroup of a finite group G, and H a P subgroup such that HP is equal to PH, then H is contained in P. So I have used many results here, and now I'm coming to the statement of CLO second and CLO third theorem. And before saying the statement, one definition, that is a normalizer of a group, I want to define here. That is in a brief, I'm writing that what is a NGP, where P is a CLOP subgroup. I'm going to define what is a NGP, that is G belongs to G, such that GP is equal to PG. Here NGP is called what? Normalizer of P in G. And we can define it as, for any group, that is NGH, that is what? G belongs to G, such that G of H is equal to H of G, where H is any subgroup of G. So my obvious question is that, okay, let G be a group and H is equal to trivial group, then what is NGH? Anybody? Okay, good. That is G. You can see that. And one result also, I'm saying that, let P be a CLOP subgroup of a finite group G, then NGP contains a unique CLOP subgroup. Now I'm coming to the Cello second and Cello third theorem, and I'm writing this in a combined form, Cello second and Cello third theorem. And of course, this is a theorem related to finite groups. It is what let G be a finite group and P divides order of G, where P is a prime. Then the set of all Cello P subgroups of G form a single complete conjugacy class. It means that conjugate of a Cello P subgroup is a Cello P subgroup. And if any two Cello P subgroups are given, they are conjugate to each other. It means that I am writing here. That is conjugate of a Cello P subgroup is a Cello P subgroup, and any two Cello P subgroup of G are conjugate. This is a, you can say that Cello second theorem. And what is a Cello third? One more result. Further, the number M of Cello subgroups of G is of the form M is equal to 1 plus K into P. This M is congruent to 1 mod P. So what we have seen here from Cello's first theorem, Cello's second theorem, Cello's third theorem, and some propositions which I have stated, some properties, results, or corollaries, what you want, you can say that. Number one, if P to the power M divides order of G and P to the power M plus 1 does not divide order of G, then all Cello P subgroups of G are of order P to the power M. This is the first result. Second result, the number M, which is 1 plus K into P of Cello P subgroups of G is a divisor of order of G. And third one, if P is a prime dividing order of G such that 1 plus K into P dividing order of G implies that 1 plus K into P is equal to 1. Means that what? Then there exists a unique Cello P subgroup of G which is normal. And number 4 result, that is, let H be a normal P subgroup of G, then H is contained in each Cello P subgroup of G. It means that is intersection of all Cello P subgroups is the largest P subgroup of G which is normal in G. This is using last result related to Cello theorem, a finite for today's lecture. Finite group G is direct product of its Cello subgroups if and only if they are all normal. I'm coming to a question, that is, what if a group is given whose order is 15, then what we can say about the group? Anybody from you? Yes. Yes. Piyush. Okay. Thank you. If order of G is 15, then it is cyclic. Why? Because if I'm saying that 15 is what? 3 into 5. So we have Cello 3 subgroups in G and Cello 5 subgroups in G. So we have Cello 3 subgroups. Okay. And what is the order of Cello 3 subgroup? That is 3. Okay. Because 3 divides 15, but 3 square doesn't divide 15. So the order of Cello 3 subgroup is 3. And what are the numbers of distinct CeLO 3 subgroups? So number of distinct CeLO 3 subgroups is of the form 1 plus k into 3 and 1 plus k into 3 must divide order of G, which is here 15. So what is the possibility? If you are taking k is equal to 0, then it is 1. It is okay. But instead of 0, if you are taking any value of k, then the number 1 plus k into 3 doesn't divide 15. So the number of CeLO 3 subgroup is 1. It means it is a unique CeLO 3 subgroup. That is, it is normal. This implies that CeLO 3 subgroup is normal. Similar remark for CeLO 5 subgroups. And since order of a CeLO 3 subgroup is 3 and order of CeLO 5 subgroup is 5, and both are groups of a prime order, so they are cyclic, and intersection of these two subgroups are trivial subgroup, so we can say that G can be written as direct product of CeLO 3 subgroup and CeLO 5 subgroup. So we can say that here G can be think as direct product of CeLO 3 subgroup and CeLO 5 subgroups, which are cyclic groups hence G is cyclic. It means we have only one subgroup of order 15, that is what? Z15. Because if we have chosen any group of order 15, then it is isomorphic to Z15. Now I am coming to result related to solvable groups. So one question is very simple here, that is, let G be a group of order P into Q, where P and Q are primes then G is solvable. Solution is quite simple, and I think yesterday or day before yesterday, Dr. Lakshmikant has proved one result that if G be a group and H a normal subgroup of G, such that G by H and H both are solvable groups, then G is solvable. So we will use these results now. Here it is written that P and Q are primes. Then we have two cases. One is that P is equal to Q, and another is P is a different from Q. So case one, if P is equal to Q, then order of G is equal to P square, and this implies that G is abelian, and we have seen that every abelian group is solvable, so G is solvable. Case 2, if P is a different from Q, then without loss of generality, we can assume that then without loss of Q is greater than P, then what we find, then number of Cello Q subgroup is what? 1, because 1 plus K into Q must divide P into Q, and only possibility of the value 1 plus K into Q is equal to 1. And if it is 1, it means that Cello Q subgroup is normal. Therefore, Cello Q subgroup, say it is capital Q, is normal. And order of Q is what? That is Q. That is Q is cyclic. This implies that Q is abelian. This implies that Q is solvable. So we can think about what is order of G by Q. That is P. This implies that G by Q is cyclic, and so G by Q is solvable. So this is 1, suppose this is a 2. From 1 and 2, we have Q is solvable, G by Q is solvable, G is That is, every group of order P into Q is solvable. One more result I want to state here, only 2 minutes. So that is a question, another question, that is, if order of G is suppose 100, then what we can say about the solvability of G. So it is again quite simple. That is, you can write 100 as 2 square into 5 square, and you can think about Cello 5 subgroups. So number of Cello 5 subgroups of the form 1 plus k into 5, such that 1 plus k into 5 must divide 100. And we can see that the only possibility is that the only is that 1 plus k into 5 is equal to 1. So Cello 5 subgroup is unique, hence normal. And order of Cello 5 subgroup is 5 square, that is 25. It is a prime square. This implies that Cello 5 subgroup is abelian, hence solvable. Say it is P. Then think about order of G by P, which is 4. That is 2 square. So whatever the group is, it is again G by P is abelian, hence it is solvable. So here P is solvable, G by P is solvable, therefore G is solvable. Hence, group of order 100 is solvable. Thank you for today's lecture, listening quietly, and we will meet tomorrow for a next lecture.
Thank you so much, sir, for such a nice lecture. Sir, kindly announce the program
Okay.
for the second session.
Yeah. So after 5 minutes, we will meet, and Dr. Vivek Kumar Jain will give the second lecture. So after 5 minutes, we will meet again. Coming. Okay. I will talk to Vivek sir, then Vivek sir, you are.
Yes, I am here.
Yes. Okay. Now I invite Dr. Vivek Kumar Jain for his next lecture. Dr. Jain.
Thank you, sir. Okay, so good afternoon, everybody. Let me first share my screen and then we will start. So are you able to see my shared screen?
Yes.
So now today we will talk about normalizer condition. One second. Okay, so this is normalizer condition. So now what is normalizer condition? So suppose G is a group. Suppose G is a group and H is a subgroup of the group G. We define a sequence of subgroups. Define a sequence of subgroups and we will denote those subgroups by N, G, N, H, where N belongs to N union 0. कैसे define करेंगे इसको? So how will we define this sequence of subgroups? We will define this sequence of subgroups by induction. So for induction, we need to define the first term. Define the first term to be H itself. And if NG MH is defined, if this is defined, then NG M plus 1 H is defined as the normalizer of NGMH. So once the first term is defined, NG0H is H, then the second term will be defined through this. So inductively, we can say that we have defined the whole sequence. So now what is the sequence? The first term is this. And you know the subgroup is always contained in its normalizer and also normal in its normalizer. So the second term, this 1H. So this is H and this is normalizer of H. These are equal. And then the third term is NG2H and so on. So what will be third term? It will be the normalizer of H and so on. So we have defined a sequence, and this sequence, the elements of this sequence are H, normalizer H, and normalizer of H, and so on. Okay. Now, there is a result. If G is a nilpotent group of class N, so let me write it as a preposition. If G is a nilpotent group of class N, then normalizer NGNH is equal to G for all subgroups H of G. Or you may write it like this. Let me. For all H subgroup of G. Okay, it means if you have a nilpotent group of class N, then this sequence of subgroups which you have defined will terminate to G. So at the nth stage, NGNH will become G. So let us prove it. So suppose G is a nilpotent group of class N, and H is a subgroup of G. Okay. To prove this result, I'm going to make a claim, and that claim is, if I take ZRG, you remember ZRG is a term of upper central series of G. This is contained in this for all R in N union 0. This is our claim. Let us prove this claim. Proof of claim. So we will prove it by induction on R. The proof of the claim is by induction on R. Okay. So suppose, we need to show for R is equal to 0. So what is set 0G? So what is Z0G? Z0G is trivial. Okay. And Z0G is trivial. So it is contained in H. And H is NG0H. So for R is equal to 0, this is true. For R is equal to 0. This claim is true. Suppose by induction, hypothesis, Zm G is contained in NGMH. Okay. So what we have to show, we have to show Zm plus 1G is contained in NGM plus 1H. So we have to show this thing. To show this thing, let us take one element in Zm plus 1G and we will show that that element will belongs to NGM plus 1H. Okay, so take G in Zm plus 1G. Okay, if G is in this group, then do you remember what is the definition of Zm plus 1G? By definition, what is Zm plus 1G? Zm plus 1G quotient with Zmg was defined as the center of G by Zmg. This was the definition of Zm plus 1G. So if I take G in Zm plus 1G, then G into Zmg, which is an element of this left hand side, will belongs to the center of G by Zmg. Okay, do you agree at this point? I hope there is no problem. Yes. So what does it mean? This implies G Zmg into X Zmg is equal to X Zmg into G Zmg, where X belongs to G. Or you may say for all X in G. You may say for all X in G, even then it is true for all X in G. We can write it like this. Is it okay? Okay, so what does it mean? It means that we can write it as Gx Zmg is equal to Xg Zmg, and this thing can be written as G inverse X inverse Gx Zmg is equal to Zmg for all X in G. Okay, but it means what? G inverse X inverse Gx belongs to Zmg. But we have taken Zmg to be equal to Zmg is contained in NGMH. So this is contained in NGMH. Okay. So if I take this X to be in NGMH, then what will happen? This is true for all X in G. This is true for all X in G. Okay, so it means G inverse X inverse Gx belongs to NGMH for all X in NGMH. Because it is true for all X in G, so it is also true for all X in NGMH. Now, because X is in NGMH, so this X is in this set, and this is a group. So it means that this is also in NGMH. So G inverse X inverse G belongs to NGMH. And we have taken X is in NGMH. So this X inverse will also be in NGMH. So it simply means that G belongs to the normalizer of NGMH, because it is true for all X in NGMH. Okay, so take any X in NGMH for all X in NGMH. So what does it mean? It means G belongs to NGM plus 1H. So what we have proved is that we have taken a G in Zm plus 1G, and we have shown that G belongs to NGMH, NGM plus 1H. So it simply means that this implies Zm plus 1G is contained in NGM plus 1H, and this proves the claim. Claim proved. Now, once this is proved, then because G is a nilpotent group, since G is nilpotent of class N, so what will happen? NGNH, sorry. So ZN G will become G. And once Zn G will become G, then G, which is Zn G, and it is contained in NGNH, and this implies G is equal to NGNH, because NGNH is always a subgroup of G. This is always contained in G. So G and NG, NH are equal. So, and this is something that we want to prove. See the statement of the preposition. Suppose G is a nilpotent group of class N, then, sorry, G is a nilpotent group of class N, then NGNH is equal to G for all H in G. So we have taken arbitrary H in G, and we have shown that G is equal to NGNH. So this proves our preposition. So this is proved. Is it okay? Or if you have any confusion, then you may ask. No problem. Okay. Definition. A group G is said to satisfy the normalizer condition if every proper subgroup is properly contained in its normalizer. If you want to write it in short, then we can simply say G satisfies normalizer condition. G satisfies normalizer condition means H is a subgroup of G implies, but one second. Yes, if every proper subgroup, so we have to take not equal to G, implies H is properly contained in normalizer of H. Okay. So actually that H will always be normal because each subgroup is normal in normalizer. So you may also close this, that will not be effect, but it is proper containment. So there will not be any equality here. Okay. So what can we say about nilpotent group? So we can write as a corollary, nilpotent group satisfies normalizer condition, because in the proposition 1 we have seen that if you have a nilpotent group, then if you will start taking the normalizer of a subgroup, then again normalizer, 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 and so on, then the sequence will end on G. Means if you are go on taking normalizer, 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 you will ultimately get the whole group G. So what does it mean? That normalizer is always bigger than the group, subgroup. So let me write it. Nilpotent group satisfies normalizer condition. Suppose not, suppose G is a nilpotent group, H is its proper subgroup, such that H is equal to its normalizer. Okay, normalizer condition means H will be proper subgroup of normalizer of H, but if I have assumed that it is not true, then there exists a nilpotent group and a subgroup, proper subgroup, such that H is equal to the normalizer of H. Okay, so, but in the above proposition, we have shown that if G is of nilpotent class N, so suppose G is a nilpotent group of class N, and so by above proposition, NG NH is equal to G. But once NGH is equal to H, then you will go on taking NG of NG of NGH. This will remain H. Does it make sense? But since NGH is equal to H, so NG NH will also be H. And this is a contradiction because H is not equal to G. And this contradiction arises due to our wrong assumption that G is a nilpotent and it has a subgroup H, for which normalizer of H is equal to H. So hence H will be strictly less than the normalizer of H. So what we have shown is that if we have a nilpotent group, then that nilpotent group always satisfies normalizer condition. Okay. There are some facts which we need to recall here, because we want to use it. So in the previous lecture, you have seen the Cello Theorems. So fact 1, suppose G is a finite group and P1, P2, Pk are all its distinct Cello subgroups. And PIs are normal. Means G is a finite group, P1, P2, Pk are its Cello subgroups, and each of these subgroups are normal. Then G is nothing but the internal direct product of P1, P2 and Pk. Okay, the proof is not hard because P1, P2, Pk are distinct Cello subgroups and each of these Cello subgroups are normal. So P1 is related to some prime, maybe small p1, and P2 is related to some prime small p2 and so on. So it simply means that Pi intersection with P1, P2, Pi minus 1, Pi plus 1 up to Pk is trivial because the orders of these groups are co-prime. And because Pi's are normal, so P1, P2 will be a subgroup, P1, P2, P3 will be a subgroup, and so on. And because if you will consider its order, then its order P1, P2 up to Pk, this will be a subgroup of G. And if you will consider its order will be exactly the order of G, so it will be G. So you may say that G is internal direct product of these groups. So if all the Cello subgroups are normal, then G is actually the direct product of these groups. But we know that PIs are P groups. PIs are P groups or PIs are nilpotent. Nilpotent groups. And direct product of nilpotent groups is nilpotent. So G is nilpotent. So what is this fact actually? This fact is if all Cello subgroups of a finite group are normal, then group is nilpotent. So if all Cello subgroups of a finite groups are normal, then that group will be nilpotent group. I hope there is no confusion at this point. Okay. Now there is fact number 2. Fact number 2. Suppose P is a Cello P subgroup of a finite group G. If normalizer of P is a subgroup of some subgroup H, which is a subgroup of G, then the normalizer of H will be H itself. Okay. So maybe you have not done this, or its proof is very easy actually. And okay, let me give you a hint for the proof of this fact. We have to show that normalizer of H is equal to H. We know H is always contained in the normalizer of H by definition. H is contained in the normalizer of H. And we have to show that normalizer of H is contained in H. So take X in normalizer of H. Okay. Now what will happen is that because H is normal in normalizer of H, so X inverse is equal to H. Now P is contained in H, so it simply means that XP X inverse is contained in XH X inverse, and that is H. So what does it mean? It means that P and XP X inverse are two Cello P subgroups of H. These are two Cello P subgroups of H. Okay. By Cello's theorem, we know that any two Cello subgroups are conjugate. So there exists H in H, there exists H in H such that HP H inverse will be equal to XP X inverse. Because P and XP X inverse are conjugate in H, so there exists an element H in H such that this will happen. So it simply means that H inverse XP H inverse X whole inverse is equal to P. So we have taken this H to be this side and this H to be this side, and we can write it like this. Okay, what does it mean? It means that H inverse X belongs to the normalizer of P. Okay. But how this H is? H contains the normalizer of P. So this normalizer of P is contained in H. So it simply means that H inverse X belongs to H. But H also belongs to H. H also belongs to H. So this implies X belongs to H. And that is what we want to prove, that if X belongs to the normalizer of H, then H belongs to H. So this implies that the normalizer of H is contained in H, or H is equal to the normalizer of H. So this is the fact, and we will use this fact. Once again, see what are the two facts we have seen. Fact number one is, if all Cello subgroups of a finite groups are normal, then the group is nilpotent. This is fact number one. And the fact number two is that if P is a Cello P subgroup of a finite group, and there is a subgroup which contains the normalizer of Cello P subgroup, then the normalizer of that subgroup will be itself. These are the two facts which we will use for further arguments. Now, there is a result, preposition. If a finite group satisfies normalizer condition, then all its Cello subgroups are normal. So proof is very easy. How will we prove it? If a finite group satisfies normalizer condition, so let us first assume that G is a finite group which satisfies normalizer condition. Suppose G is a finite group and G satisfies normalizer condition. Okay. What we have to show that all its Cello subgroups are normal. So suppose there is one Cello subgroup that is not normal. Suppose P is a Cello P subgroup of G and P is not normal. So we are using the method of contradiction. We have assumed opposite that P is a Cello P subgroup and P is not normal. So if P is not normal and G satisfies normalizer condition, so P will be properly contained in its normalizer and its normalizer will be contained in G properly, because if normalizer is equal to G, then the subgroup will become normal in G, and we have assumed that P is not normal. So this relation will be satisfied. P is properly contained in normalizer of P and normalizer of P will be properly contained in G. Okay. But see the above result, above fact number 2. In fact number 2, we have seen that normalizer of P, H in G, then the normalizer of H will be H. Okay. So in place of normalizer of P, if I take H to be the normalizer of P, then it simply means that the normalizer of H is equal to the normalizer of P, that is H. That is what we proved now in the fact number 2. So see it again. In the fact number 2, if I take H to be equal to, in this fact, if I take H to be normalizer of P, then even then this fact is true. So it simply means that normalizer of P is equal to normalizer of P. I hope there is no problem. Is it okay? Should I proceed? Okay. So this is true, then you can see it from here. So now, but normalizer of P is equal to normalizer of P. Okay, but what is this normalizer of P? Normalizer of P is a proper subgroup of G and its normalizer is equal to normalizer of P. This is a contradiction to the fact that G satisfies normalizer condition. G satisfies normalizer condition. And why that contradiction arises? This contradiction arises because of our wrong assumption that P is a Cello P subgroup of G, which is not normal. Hence, all Cello P subgroups are normal, and this proves our proposition. This proves our proposition. Okay. So what we have done up to now, let us summarize it. We have shown that G is nilpotent implies G satisfies normalizer condition and if G satisfies normalizer condition, we are taking the finite nilpotent group. G is finite group. Finite group. G is a finite group, and if G is a nilpotent also, then G satisfies normalizer condition. And if G satisfies normalizer condition, then we have shown that all its Cello subgroups are normal. And from the fact number 1, we have shown that all the Cello subgroups are normal in a finite group, then G is nilpotent. So what does it mean? It means that these three conditions are equivalent, if and only if. Okay, so can I put it like this? G is nilpotent if and only if G satisfies normalizer condition, if and only if all its Cello subgroups are normal, provided G is a finite. So we have shown it for finite. And this is what we have shown just. I hope there is no problem till now. This is the summary of what we have done till now. Okay, now let us come to another result, preposition. This, okay, before stating this preposition, let me write one more fact, fact number 3. And we are not going to prove this again. This fact we are not going to prove. And I think you know it. Let G be a finite P group of order P to the power n. Then for each K varying from 0 to n, there exists a subgroup H of G of order P to the power K. What does it mean actually? It simply means that if you have a finite P group of order P to the power n, then for each divisor of P to the power n, there exists a subgroup of that order. Means, it simply means that the meaning of this fact is that converse of Lagrange theorem, we'll write it in short CLT, is true for finite P groups. Okay, this fact simply means that converse of Lagrange theorem holds for finite P group. And because nilpotent groups are the direct product of these P groups, so the converse of Lagrange theorem is also true for nilpotent group. So I am writing it as exercise to verify that, show that converse of Lagrange's theorem is true for finite nilpotent group. Okay, any finite nilpotent group can be written as a direct product of its Cello P subgroups, and Cello P subgroups, for Cello P subgroup this theorem holds. So we can say that, we can prove that this theorem holds for finite P group. Okay, 1 second. There is a question that you are saying that all these three conditions are equivalent, but in third condition you are not putting if and only if condition. Maybe I am not getting properly. So okay, so let me again see this conditions. This point number 1, 2, 3 and 4 is same thing. 4 is same thing, so we can say that 3 implies 1, 1 implies 2, so 1 implies 2 implies 3, and 3 again implies 1. 3 again implies 1. That's why I am saying that these three conditions are equivalent, and this is something that is not new, that is same as 1. So this is all are equivalent. So is it okay, Ragini? Okay. Okay. So there is another theorem, let us prove. A finite group is nilpotent if and only if all its maximal subgroups are normal. So that is another condition. A finite group is nilpotent if and only if all its maximal subgroups are nilpotent. Okay, so let us prove it. Proof. Suppose G is a finite nilpotent group. Okay, so G is a finite nilpotent group. Now we will show that all its maximal subgroups are normal. Further, suppose H is a maximal subgroup of G. Okay. Now we have shown that if G is a finite nilpotent group, then this G will satisfy normalizer condition. Since G satisfies normalizer condition, so H will be properly contained in the normalizer of H. And this normalizer of H is a subgroup of G. But because H is maximal subgroup, by the definition of maximal subgroup, this normalizer has to be equal to G. So this simply means that is normalizer of H is equal to G. Hence H is normal in G. Is it okay? What we have shown is that G is a finite nilpotent group. We have assumed that H is a maximal subgroup of G. Because G is nilpotent, so G satisfies normalizer condition. So the normalizer of H will be, so H will be properly contained in the normalizer of H. But H is maximal. It cannot be contained in any another subgroup properly. So it means that normalizer of H has to be equal to G. And once normalizer of H is G, it means H is normal in G. So we have proved one way. We have proved that forward implication, this holds. Now we are going to prove that if all its subgroups are, maximal subgroups are normal, then G will be nilpotent. Okay. So conversely, suppose that all maximal subgroups are normal. So we have to show that G is nilpotent. To show that G is nilpotent, it is sufficient to show that all its Cello subgroups are normal. Okay, so we will show that all Cello subgroups of G are normal. So take a Cello subgroup. So suppose P is a Cello P subgroup of G. We will show that it is normal. If P is not normal, or you may proceed like this. If P is normal, then there is nothing to do. Suppose P is not. Suppose P is not normal. Not normal in G. Okay. If P is not normal in G, then there will be normalizer of P. And this normalizer of P will be a proper subgroup of G. Because if normalizer will be equal to G, then P will become normal. So then, but every proper subgroup is contained in some maximal subgroup. So there exists a maximal subgroup H such that this normalizer of P is contained in H. Okay. But as you can see that we have proved one fact. If P is a Cello subgroup and its normalizer is contained in some subgroup, then what will be the normalizer of that subgroup? Then the normalizer of H is equal to H. See, we have shown this. Let me show it again to you. That we have proved that if P is a Cello P subgroup of a finite group G and the normalizer is contained in some subgroup H, then the normalizer of that subgroup will be H itself. That subgroup will be H itself. So it means the normalizer of H is H. Okay. But what is our assumption? Our assumption is that conversely, suppose that all maximal subgroups are normal and H is maximal. And maximal subgroups are normal means its normalizer is equal to G. But H is a maximal and maximal subgroup is always proper. This is a contradiction. This is a contradiction. And this contradiction arises because of our wrong assumption. And what was our assumption? Suppose P is not normal in G. Hence, P is normal in G. So all Cello subgroups are normal. Since all Cello subgroups are normal, so G is nilpotent. Okay, so let us again summarize what we have done. What are the things which we have proved? Let us summarize. G is finite group. Okay, fact number 1, G is nilpotent. Fact number 2, G satisfies normalizer condition. Condition number 3, all Cello subgroups are normal okay, which is also same thing can be written as G is direct product of its Cello subgroup and fifth one is that all maximal subgroups of G, all maximal subgroups G are normal. Okay, so what we have shown is that these all are equivalent. 1 if and only if 2, if and only if 3, if and only 4, and if and only 5. These all are equivalent. This is what we have shown. Okay, so let us stop today at this point, and tomorrow we will start with the Fretney subgroup example and its properties. So thanks to all of you, and now over to organizers.
Vivek sir for a nice lecture. And we will meet tomorrow at 3 p.m. Thank you, all of you.
Thank you, sir.